Okay, let's analyze this circuit, which is a BJT circuit with specifically we are using the NPN transistor as the direction of the arrow shows. The current flows from collector to emitter. There are 3 pins of BJT: collector, base, and the emitter. Emitter is tied to ground. To the base, we are applying an externally applied input signal through this capacitor, coupling capacitor C1. From the collector, we are taking the output by means of again using coupling capacitor C2. So C1 and C2 are our coupling capacitors. From the collector pin, we are using the resistor as shown. The one end of the resistor is tied to the voltage supply VCC that is connected, and from that voltage supply we are drawing the current into the circuit. Now this is an NPN transistor. So if we want to use this transistor as a small signal amplifier, we want to make sure that its base emitter junction VBE is forward bias and its base collector junction VBC is a reverse bias. In another word, in order the transistor to be operated in the active mode or linear region, your voltage at the collector should be equal to or greater than the base emitter voltage. The base emitter voltage, assuming this transistor is silicon, is approximately 0.65 to 0.7 volts. Now, there is one more important point to be noted here. From the collector, we are using the resistor RF till the base pin. So this resistor is serving the 2 purposes. One, it is helping us to set the bias point. So that's the first purpose of using RF. Second, sets the feedback in the circuit. Now we'll see. So this is the uses of resistor RF, which is feedback resistor, or we also called as the bias setting resistor. Now there is a load resistance RC of this circuit right here. So because we apply an input signal, there is an input current I1 will flow into the circuit. That current is actually becoming IB here. For a moment, we assume there is no feedback. So the current here is IB. Now the current here is IE, that is emitter current, and the collector current IC is flowing in the collector pin. And that is which is nothing but the current flowing through the through the RC. Now there is a feedback. It means we are sensing the voltage at the collector pin, and using the resistor RF, we are converting that to the current IF. That IF comes here and it sums with the input current, and therefore the current IB comes here. So we can write the expression here. Let's say this is I1, this is IF, and this is IB. And IB would be IF plus I1. This is the correct current I. That's the current IC. That's the current IE. And we know that IE will be IB plus IC. And IB will be IC divided by beta, where beta is equal to HFE is equal to DC current gain of the transistor. Okay. So now what is the output voltage? For the output voltage, we can write the expression. It is equal to VCC minus I times RC, and I is IC. Or we can say that your I is equal to IF plus IC, because this I is being split into the 2 parts, IC and the IF. Okay. So that's how you can get that. Now, what kind of feedback is this? What kind of feedback is this? So we say that we are sensing the output voltage, we are converting it to a current. So if we can draw the, if we can actually draw the negative feedback amplifier circuit. So we have this AOL, that is open loop gain. Then we have this feedback network beta. Okay. We have this mixer, and then we have this input signal Vi, and then the output signal here is actually your current actually, right? So you basically don't sum the you basically have the Vi, and because of that you have the current II here. That is the current you will have. That is the input current. Let me write here. So it will be II. Okay, and then you have this feedback current IF here, and then II plus IF will be the IB, that is the control current or the error current. The output of this is basically the voltage, and you are sensing the voltage and giving it to the resistor. So the beta feedback network is RF, okay, and IF is the output of it, and the input is the VI. So beta will be IF divided by VO. So it is working as a transconductance property. Transconductance. And here the amplifier is actually, you can call it as the AOL, would be the ratio of output divided by input current IB. So it is like trans resistance V by I, trans resistance. Or you can also say that AOL, because II is a function of VI, input voltage. So you can have this gain also. So it is also called as voltage amplifier. So it will be voltage amplifier. Okay, so depending on whether you just take the gain as a ratio of output voltage divided by input current, or output voltage divided by the input voltage, VO over VI or VO over IB. So that's how you will get that. What would be the small signal model of this? So let's say this is R pi, that is the base resistance across which you have this VBE. This is your base pin. Emitter pin is kind of grounded. So you actually see that. Then you have this, you can model this collector current, which is GM times VBE. That is your collector current. And then you have, this is collector pin. Then you have this resistor RC, which is connected to the ground. Okay. And then from the collector to base pin, you have the feedback. So here actually you can say I have this RF, and this is the current IF. So that's the small signal model. So what you see here, if you actually want to see the effect of feedback, you have to actually analyze that. Okay, so let me just find out. So this is basically called as voltage shunt feedback. Okay, or also called as voltage current feedback. Okay, or also called as series shunt feedback. Okay, because you're sensing the voltage quantity in series and you're applying the current in parallel. to the input side. So that's how you actually have analyzed this circuit. Now you can make sure that the transistor operates in active region, and you're all set to use it as a class A small signal amplifier. So hope you like this video, you found this useful. If you did so, click the like button, share with others for wider reach, and stay tuned for more informative contents like this. Till then, wish you happy learning. I give you an exercise. Calculate the VO over VI and VO over IB, uh, or not IB actually, VO over II, these two gains of from the small signal model. Okay, so here is the output voltage, here is your input voltage. Okay.